We're about to start a chapter on isomers. So let's do a quick review of what we've already learned about isomers. I do not know if you can hear what's going on in the background, but my cats are having an absolute conniption fit. It sounds like somebody's dying, but it's just cats. So first of all, let's review the term isomers. Isomers we defined as it's a pair of molecules, or it could be more than two. So it's a set of molecules that have the same molecular formula, which means that they are going to have the same number of each type of atom. But they are different, isomers are different because they have something different about their structure. And we learned about one type of isomer already, but we're about to learn a second type of isomer as well. So the type that we've already learned, we called constitutional isomers. Constitutional isomers are also sometimes called structural isomers. And what we learned about constitutional isomers was that they had something different in the way the atoms were connected to each other. So, for example, here's two molecules that are constitutional isomers of each other. They have the same number of atoms, the same number of each type of atom, so they have the same molecular formula. They are both C5H12. But they have a different connection of atoms. The molecule on the left, pentane, is just a straight continuous chain of 5 carbon atoms, whereas the molecule on the right is 4 carbon atoms in a row, and the 5th carbon atom is branching off of that row. So that's constitutional isomers. The other type of isomer that you've seen before, but we haven't given it a name yet, is called a stereoisomer. Stereoisomers have the same connection of atoms. So they're different from constitutional isomers. They have the same connection. They also have the same molecular formula because that's the definition of isomers in general. They have the same connection, but they have a different shape. Now, initially this might be a little bit confusing because you might be thinking, if you think all the way back to week 1, when we were talking about the way in which we draw line structures, and we talked about how it didn't really matter how we drew these line structures. They were all representing the same molecule. So these that I just drew these for, they are all the same. They are all identical to each other. These are not isomers. These are just 4 different ways to draw the exact same molecule. And for these molecules, the shape in which we draw it does not matter. Shape doesn't matter for these boring alkanes. Alkanes, meaning that we've just got a bunch of carbon-carbon single bonds, no carbon-carbon double bonds. Here are two examples of stereoisomers. When you have a carbon-carbon double bond in the molecule, we learned about this last week when we were talking about cis and trans. The molecule, the double bond in the molecule is not free to twist around and rotate. That type of motion is not allowed, which means that these two molecules are not interconvertible. The molecule on the left cannot twist itself around and turn into the molecule on the right. That's not going to be allowed. So the molecule on the left is totally different from the molecule on the right in terms of its shape. And when we were learning this, we learned about like draw a line through the double bond and ask yourself, are the hydrogen atoms or whatever you can find, are they on the same side of the line or are they on opposite sides of the line? When they're on opposite sides of the line, we call the molecule the trans isomer. When they're on the same side of the line, we call the molecule the cis isomer. So these are two molecules that have the exact same order of connection. They have a that was not what I wanted to do. They have a CH3 followed by a CH that is double bonded to another CH followed by a CH3. So they have the same connection, but they have a different shape, cis versus trans.